Hello, I am Ali Raj and I use Docker every day to manage a system with millions of users and hundreds of containers. In this course, I will show you how to get started using Docker. First, I will take a look at the Docker flow and how to work with containers. Then, I will build some Docker images of our own. After then, I will look at the networking and some more in-depth part of how Docker works. Throughout this course, I will put you in some hands-on experience from my time working with Docker in production. So let's go. For following along with this course, I am gonna assume you have some exposure to a command line somewhere. Basic networking will help you quite a bit and Bash and Linux shell scripting will be really nice, so they are not required. Docker creates up a running Linux system into a small container, each of which is in own sealed little world with its own program and its own everything, all isolated from anything else. These containers are designed to be portable so they can be shipped from one place to any other, and Docker does the work of getting these containers to and from your system. Docker also builds these containers for you, and it is a social platform to help you find and share containers with others who may have already built with very similar work that you can build on the top of that. And let's get it up front that Docker is not virtual machine. There are only a single operating system running. That operating system is just carved up into isolating little spaces. A container is a self-contained sealed unit of software. It has everything in it that is needed to run that code. I mean all of it. Batteries, including operating system, including all of its code, all of its configuration file, containing all the process within the container. It has all of the networking to allow these container to talk to other container that they are supposed to be able to talk to and nothing else. It has all the dependency that your system needs bundled up in that container, and it even includes just enough of the operating system to run your code. So the way it works, it takes all the services that make up a Linux server, networking, storage, code, interprocess communication, the whole works, and it makes a copy of that in the Linux kernel for each container. So each container has its own little world that it can't see out of and the other container can't see in. You might have one container on a system running Red Hat Linux server, a database through a virtual network to any other container running Ubuntu Linux, running a web server that talks to that database, and that web server might also be taken to the cache server that ran in a SUSE Linux based container. The important part to understand is it just doesn't matter which Linux each container is running on, it just has to be a Linux, and Docker is the program which manages all of this, sets it up, monitor it, and tear it down when it's no longer needed. Docker is a client program named Docker. It is a command you type at the terminal. It also a server program that listens for messages from that command and manages the running Linux system. Docker has a program which builds container from code. It takes your code along with its dependency and bundle it up and then seals it into a container and let its services that distribute these containers across the internet and make it so you can find other work and the right people can find your work. There is also a company that make all of these. Docker's primary job is to manage a Linux server and start and stop your container on it as required. Most of us don't work on laptop running Linux all the time. Many people use a virtual machine running on their laptop to act as Linux server and run the server side of Docker. Docker provides tools that make managing that is very nearly transparent. To take a look at how that works, first we start with your computer. This is the thing you are physically typing on. On that, in your terminal, you interact with a program named Docker. That Docker is the client that is connecting to a program named Docker that is servers that controlling a Linux virtual machine. So also on your laptop, you have a Linux virtual machine being managed by Docker for Windows or Docker for Mac, depending on your platform. Once you have it installed, you can click on the little wheel over here and see that it's running. You usually don't have to interact with this very often other than the starting and stopping it. It is fairly well automated at this point. Let's take a look at Docker in action. Over here is my terminal. I am gonna run Docker. To run the Docker client, run is the command, and I am just gonna run the hello world container provided by Docker. All it does is print out some information about Docker. See it there? It doesn't have it already locally, so it is automatically fetching it from the internet, downloading everything required to run it, and then running it. Oh, it said hello. There have been several evolutions of the Docker desktop experience over the year, starting with boot to Docker and then proceeding all the way up to the modern tool Docker Desktop. If you have one of the intermediate tools like Docker for Windows, Docker for Mac, Docker Toolbox, anything that give you a terminal where you can run Docker commands successfully, you are good to go and can skip the rest of the course. If you have truly old boot to Docker tool installed, it is too old to complete this course and you are going to need to completely remove it and install Docker Desktop. No, this is perfectly good opportunity to upgrade anyway. Docker Desktop is better in most regard, so it's probably worth taking the time to go ahead and get up to date. So now let's get this installed. Alright, let's go ahead and install Docker on this Mac. I am gonna to head over to the Google and give a search for Docker Desktop. Alright, the first link we find here, which is docker.com/product/desktop. Of course, the link may change over time. Now we are going to head and click on the download Docker for Mac and Windows. These used to be a separate. Now you start off in the same place for both platforms. It's going to ask me to log into the Docker. This is the Docker ID you will use for publishing images to the world and accessing private images. It's not super critical what you choose here, but it is definitely worth signing up. So if you don't have a Docker ID already, go ahead and click on the sign up button down here and go through the flow. Need to go ahead and enter my password. Okay. Now let's click download Docker for Mac. Okay, I'm gonna to click on it. Alright, now let's grab Docker and drag into the application folder. Okay, now I can close that and go ahead and run Docker from the Finder. Yes, I want to open Docker that I download from the internet. Okay, now here we get to use that Docker ID again. This is option here. You can log in now and you can log in later, but it's definitely worth doing and it will remember your login. It is a good thing to do while Docker is busy downloading a virtual machine in the background and getting your computer set up. So, okay, Docker is now up and running and you can in general you can click on the whole up here and you can see what's going on with your Docker. If things start breaking or just seem a little weird, this option right down here is your friend that will restart the Docker virtual machine running on your computer and generally fixes about 99% of the problem. Now in the extreme cases, go ahead and open it again. Alright, let's go to see in this section. To actually run Docker, head on over to the terminal and run Docker command. So we can see just print out a little information on what Docker can do. Now if you get a message here saying cannot connect to something, socket not available, etc. Then look up here to make sure Docker has actually finished creating starting and hit the restart button. If it has not, okay, Docker info just tell you a little bit and confirm that the server side of the Docker is indeed running the sign starting up here. Let's run something. Docker run hello world. Alright, it did not find the hello world image locally, so it automatically downloaded it from the internet. Started up a container and that container printed out a little information about how Docker works. So we can say we have got Docker working on this computer and we are ready to go for this course. Next, let's get started running on this Windows machine. I am going to go ahead and give a search for Docker Desktop. Okay, and head on over the docker.com/product/Docker Desktop. The URL on this landing page may change over time. Let's click on Docker Desktop. Okay, now I'm going to take a moment to log into my Docker account. If you don't have a Docker ID, it's well worth setting it up. This is what you will use to push and pull private images, so it is helpful beyond just downloading. If you don't have an account already, hit the sign up button and go ahead and make one. Alright, I'm going to enter my ID and hit sign in. Okay, download Docker Desktop for Windows. Okay, go ahead and run that. Okay, now that it is installing, see this box where it says use Windows container instead of Linux container. We want to explicitly not check that. In this course, we are going to use Linux container regardless of the platform we are on. One of the key points of Docker is that it lets you be a cross-platform. Okay, now I am going to go ahead and hit the close and log out. So now that I'm logged back in, Docker has starting up and informed me there is a new update available. I am gonna to go ahead and install that one a little bit later. This might be a good time for you to install it if you would like. Okay, Docker needs to activate Hyper-V Windows Virtual Platform so it can create the Linux container on a Windows environment. This will probably require you to reboot your computer. I am going to go ahead and click OK. Let's pick this back up once my computer has rebooted. Great. Now that my computer rebooted, I am ready to use Docker. So to check on the state of Docker, you can go ahead down there, click on the tray. If you see the whale there, you are good to go. if things doesn't seem to be working right on the otherwise stuck you get error about cannot connect to socket. Give this guy a right click and right there that restart button will restart the virtual machine on which Linux container live, and that fixes about 95% of the problem. The other 5% problem may be hit the quit and restart option. Alright, so let's go ahead and use this. To use Docker, I am going to bring up the command prompt and run docker info. This just print out the information about both the client side and server side of the Docker. So if it works, you know your system good to go. But that's a little boring. Let's do something more interesting. Docker run hello world. It didn't find the hello world image locally. So it reached out to the internet, download the system and run it. This printed out a little information about Docker and how Docker works. Alright, your Windows machine is ready to go for this course. Installing Docker on Linux is much more straightforward than other platforms. Since it's just any other program on Linux, you can go ahead and just install it like any other program. I am running Ubuntu, so I am going to search for installing Docker on Ubuntu and head over to the official Docker installation guide for Docker Ubuntu. If you are running Red Hat or one of these other distributions, the process will be very similar, but you will land on a different page. Okay, the first thing I am gonna do is check that I meet the requirements. Most modern Linux system will. If you have previously installed version of Docker that are not called the Docker/CE, go ahead and remove all those previous versions. Trust me, Docker CE is much more modern and going to work better for you. Okay, the first thing we are going to do is to make sure our system has its dependency generally up to date. I am going to copy, switch over to the terminal and paste it in. Note that I have got that we are going to go ahead and install the dependency that need to be in the place before we can add the Docker organization as a source of software for our computer. Copy paste, we want to install HTTPS transport, a bunch of certificate authority. Make sure we have the URL for one of the step later on, and a collection of generally useful software properties common. If your computer tells you are that already installed, then it's good, you are good to go. No, that has been done. This is an important step. I am going to go ahead and tell my system that it should trust software provided by the Docker organization. Copy page 18. What this is going to do is fetch the cryptographic signing in key of the Docker organization from them and tell my computer to import this as a key that is trusted to provide software to the system. So it's going to download the key, then over here it's going to take the content of the key and pipe it to the apt/key command, which add a trusted source. Remember the dash at the end of the command. If you are pasting it in, it doesn't work. Sometimes it's because that get left off. Okay, and now the next important step is to add the Docker organization as a source of software for this computer. Go ahead and copy that command, paste it in. What this does, it is calling apt-add-repository, which adds an official source of software, saying we are going to add a source of Debian packages for the, in this case, AMD 64 architecture that almost certainly what you will be using, then the URL of where Docker provides their software. This little bit here, the isv release command inside a subshell is just a little bit of the shell magic to automatically detect which version of Ubuntu your system is running and fetch the appropriate packages. Okay, now with all that out of the way, we are nearly done and refresh the dependency again. apt-get update, remember the sudo. Now the magic moment, apt-get install docker-ce. With that done, for most people and most purpose, you are done with this guide. If you need a specific version of Docker for compatibility with something else, then you can keep going on. So now let's see if it is work. Docker run hello-world. I need to add my user to the list of users who are allowed to run Docker without putting sudo at the beginning. If I take that same command that the sudo docker run, then I see it to go. But that's not very convenient. Let's go ahead and make that work. Scrolling down to the bottom here, under the next tab, there is a post installation guide. Clicking on that and scrolling down to the manage Docker has a non-root user. All we have to do is run a couple of commands here, copy paste. I am gonna to create group of running Docker command. It is okay if it is already exists. Then paste, then I am gonna go ahead and add my user to that group. $user here will resolve by the shell to the username and you are logged in right now. Okay, this next step gets a lot of people. You need to do something that causes you to new login contest before the group that changes take effect. The easiest way to do is just log out and log in back again. Log out, open up my terminal, and I'm going to run docker run hello dash word go. Then we have it. Docker started up a container, ran a process called hello dashboard that introduced you to the Docker, and that's was done. It's working. Note that we have got Docker installed and take a little bit about what Docker is. Let's talk about what Docker does. The Docker flow, the fundamental concept in Docker, it all begins with an image. An image is every file that make up just enough of the operating system to do what you need to do. Traditionally, you would install a whole operating system with everything for each application you do. With Docker, you pared it way down so that it will have a little container with just enough of the operating system to do what you need to do, and you can have lots of these efficiently on your computer. So let's take a look at the Docker images. Amazingly creatively, the command to look into your Docker images is Docker images. It's a little bit squished. Let me stretch that out of for us. There we go. So here we have where the images came from, the repository. A tag is a version number. The repository for the image is where it came from. In this case, it was named Ubuntu. This is the example we use in the installation movie. Tag is the version of it. In this case, is the tag latest, and then this image's ID, which is the internal Docker representation of this image. So you could always refer to this image by the combination of its name and its tag. Ubuntu latest in any Docker command, or you can refer to it by its number. It's useful to be able to refer to them by a number because sometimes they don't have the name. They don't have to. But if they do have a name, it is a little more convenient to use it. Now what good is an image if not to do something with it? The docker run command takes an image and turns it to a living running container with a process in it that's doing something. Hopefully something useful, but at least something. So let's take a look at running an image to make a container. So note that I have got my image. I want to actually run something in it, so I am gonna use the ever conveniently named docker run, and I'm gonna put this couple of flag in here. T stands for the terminal interactive. It's just the cause it have all the full terminal within the image so that you can run the shell and get things like a tab completion and formatting to work correctly. When you are running command by typing on a keyboard inside an image, this is very useful tag to put in. Most of the other time you don't need it. TI for the terminal interactive. Now we need to say which image we will like to run this thing in. Ubuntu with the latest tag. What would we like to do? Well, since I am gonna be typing on this keyboard, I am just gonna run the bash shell in my image. Alright, I am in my image. If I look around, I am in the Ubuntu environment. Let's take a look at the standard plate to see what distribution I am using. I am using Ubuntu 1604 here. To exit this, you can type exit or you can just press Ctrl D. So now we have a running image. I am gonna run the image again and bring up any other terminal so we can take a look at it from the outside. There we are. I have got my Ubuntu container running in the terminal on the left here. So on the right, I am gonna use the docker ps command to take a look at the running image. So let's just run docker ps. Now on my screen it's look a little squished here, and I prefer to look at things vertically. So just for my personal preferences, I have defined a format string which will print them out vertically instead of horizontally. This is completely optional. You don't have to use it, but some people will find it more convenient. We will take a look at that format string in a moment. For now, let's take a look at what we got here. So our container, the running container, has an ID which is different than the image ID what was used to run it from. Images have one set of ID, container have their own set of ID. They don't overlap, and there is no place in Docker where you can interchange image and container ID. At least not that I know. So let's the idea of the container here. We can see the images that was made from the command that's running in it. And when it is created, the status and its name. Since I did not specify a name when I started this container, Docker helpfully made me a nice creative one. So that formatting string I mentioned, this is just a convenience for my personal preferences. It looks like this. You might see things differently in the terminal on your computer if you just run docker ps without the dash format. You are getting the same information, you are just getting it laid out horizontally instead of vertically. And you can freely play with the format string to the format output of the most docker command. In almost any way, it is a very flexible even if it doesn't look very pretty. Alright, now we have a running container. So this next part is sort of important. So what makes Docker different from the virtual machine of running things on a real computer? When you are inside a container, you start from an image and that image is fixed. It doesn't change. When I make a container from an image, I did not change the image. So in my container over here, which I made from Ubuntu image, Ubuntu latest image, I made this container. I am gonna create a file. So we are at the root of the file system. I am gonna make a big file. The touch command just make a pretty blank file. Make a blank file called the my file here in the big letter. If I do ls right here, there is my file here. If I go over to this other terminal, if I start up any other container from the same image that I made this one from, so I'm just gonna run the same command again, docker run -ti to make it pretty Ubuntu latest batch. So I have started from the same place and made a new container. Do on ls, I do not see that file. See my file here shows up on this side. It is in this container but is not in any other container made from the same image. And if I exit this container and I start it again, the file is not there. Files go into the container but that does not put them back into the image that the container came from. They stay in that container. So we can see we went from an image to running container. When we run that container again, we got the same thing we get for the first time. And that's the whole point of images. It is they are a fixed point where you know everything good and you can always start from there. Now when you have got a running container, you make changes to that container. You put file there. It is very useful. When you want to be able to actually save those, the next step in the Docker file is a stopped container. So the container that's running is alive. It has a process in it. When that process exits, the container is still there. So that file I created a moment ago, when I exited that container is still there. I can go back and find it. It did not get deleted. It's just that it's currently in a stopped container. So I can look at the most recently exit container with the docker ps command. Just like I do when I want to look at the running container, except stopped container don't show up by default. To see stopped container, I can specify the -a argument to see all the container, a for all, and if I just want to see the last container to exit, I can do docker ps-i. Now since I just exited a container right there, I am gonna save docker ps-i because I want to look at the last one. Let me put in my format argument to make it fit nicely on my screen. I see I have container. That's the container ID from this one right up here that I just exited. You see the images that I was started from the command. I had run bash. I made it 5 minutes ago and it exited with an exit code of 127. That's just the return value of whatever process you ran. 0 generally means success. In that case, it was a shell and I exited it so that it returned 1 to 7. Looking at this exit code can be a good clue, so has why a container died. If you expected a container to be running and you find to be stopped from same reason, it can often give you a clue, right? This container does not have any networking going on and Docker can be newly made up a name for us. Now say I got a stopped container that has a file in it I want to use for the future. I started from the base image. I installed my own software. I have got a container that has my software installed on it. The next step is the docker commit command. That takes container and makes images out of them. It doesn't delete the container and the container is still there. Now we have an image with the same content that was in that container. So docker run and docker commits are the complementary to each other. Docker run takes images to container and docker commits take container back to new images. It doesn't override the image that the container was made from. So now we can make a new thing. Let me go ahead and show you that. If I start with the Ubuntu image docker run -ti Ubuntu, the latest tag is actually optional. If you don't specify a tag, Docker will fill in the world latest for you. So I am gonna go ahead and omit that. Run a container. Let's take a look. Totally blank normal Ubuntu container. I am gonna make a file. My pattern file. Okay, know that I have finished editing this container. Going to exit by pressing Ctrl D. You can also just type exit. I am gonna to look at the most recently exited container. There I see. Alright, docker commit and I am gonna grab that container ID. Copy, paste. So I have got a container ID. I'm just gonna make an image out of it. Boom. I just got an image ID out of it. Looks very different from my container ID. Now I have made a new image. The original Ubuntu image is unchanged. I have the new image and it just has a bigger number. Not very convenient. So the last step in the docker flow is the tag command to give images name. I can say docker tag gonna grab this big name ID and everything after the colon, copy, paste in it here. And I'm gonna call this images. Alright, if I run docker images, we can see I have a new image called my image. I can say docker run ti my image and it has my important file in it. Committing images and then tagging them in such a common pattern that is actually built right into a docker command. You can skip the step about copying the image's name over to the docker tag command and just run docker commit. The name of the container, write its nice human readable name. Then you can as the next argument say the name you would like it to be tagged as. I'm gonna say let's make any other image out of that container. And I'm gonna call that image my image too and went ahead and I did the same thing. You can see it printed out the same container ID as before. Docker images and it made a new image. I just had one extra step. This is the format you should probably use in all of your day-to-day life. There is no reason to go through the extra step of doing a commit than running docker tag, but it is very important to understand that what's happening under the hood. And there we have the docker flow. Note that we have got the docker flow in mind. Let's talk about running things in docker because what it is all about. So to start off we have the most important command docker run. We have been using it a whole lot but haven't really talked about it. Docker run start a container by giving image name and process to run in that container. This is the main process to a container. When that process exists, the container done. The container is not done till that process exists. If you start other process in a container later which we will cover, the container still exists but that main process finishes. So Docker container have one main process and they can have names. If you don't give it a name, it will make one up. Let's talk about that. So if I run docker run just like example we have been using a lot, I am going to go through in some extra argument we have not used before. So I am going to go through in the dash dash rm. This is very common command. Lots of people use it all the time when you just want to run something in your container but you don't want to keep the container afterward. That say delete this container when it exits. Otherwise you just have to go and say docker run. Do your stuff, exit docker rm container name. This saves a step. Lots of people use it. You should know about it. Dash terminal interactive TI just to make things look good. Ubuntu and I am gonna to run a command to say sleep for the 5 seconds. So this will start a container. It will sit there for 5 seconds and then exits. Boom, very exciting. See the idea there, we started a process. The container existed for the duration of that process and then it was done. Now let's run a more fancy container. So I am gonna to say we are going to start a process. That process is bash the shell and I am going to give that shell an argument that say run a few things. Very often people want to say start a container that say first run this. When it finishes, run the second thing. This pattern is extremely common for that. So I am gonna to say for this example, we are going to sleep for 3 seconds and when we are done, the semicolon is bash for when you finish the first command start the second one. It's going to echo all done. Here we have one process batch which start. That batch process start the sleep command. When that's finished, it run the echo, right? So this very common when you want to start a container and have it first do one thing in the container then do any other thing in the container. All done. Now let's talk about leaving things running a container. Docker has the idea of detached container. You can start a container running and just let it go. So that is accomplished by doing docker run dash. I'm gonna to put my usual dash ti so it looks nice in the terminal Ubuntu bash. But this time I am going to go right back here. I am going to put in a dash d for detach. So that's going to start this thing running and leave it running in the background. It prints out the identifier by which you can go and find it. You don't have to use that identifier. You can also see it by running the docker ps command. Now again I have put my format argument on here make it look better on the screen. That's the optional to you and because I like to see it outputted vertically. Alright, we can see we have one container running. It has this ID 2b5 which matches that ID and it got a nice little name Suspicious William. Now from this terminal over here I am gonna to run docker attach copy Suspicious William. There I go. Now I have jumped into that container that I started over there. Then there is a special key sequence you can type. If you hit Ctrl P and Ctrl Q, it exits you out of the container by detaching you from it and then leave it running so that we can attach back again and pick up where you left off. And again, you can find your container with docker ps and you can attach back to them with container attach container slash name. Now let's say you want to run more things in a container. You started a container, it's got something running and you want to add any other process to a running container. This is really a good for debugging. Your container acting up, you just want to jump in there, figure out why. You don't get to add extra fancy stuff with this, you just start a process in it. You can't use it to add more ports or volume or any other stuff that you can do with Docker. So over here I have my Suspicious William running in this terminal and I would like to attach this terminal also to the mRC special volume. Of course, the example name will be different when you run it on your computer. So I can run docker x-ti. So I'm gonna to execute a new process in that container suspicious volume and the process. So I get an interactive shell. Alright, now I have any other shell in that container. Make a file called for. I see this file for right there. If I go over to my other terminal, there is, I really am in the same container. Now when the original container exits, which I will do by pressing Ctrl D over here, my attached process that I had exit in there, that did with the original container. Looking at the container output of a container that's already finished is something that can be very frustrating. You start up the container, it didn't work, and you want to find out what went wrong. The docker logs command is the key for this. Docker keeps the output of the container available. It keeps it around as long as you keep the container around, and you can use docker logs container dash name to look at what the output was. I'm gonna start a container to do some very important work here. I'm gonna say docker run, and I'm gonna give this container a name, for example, so that I can find it easily afterward. And I'm gonna run this as the attached container. I just want to run it in the background. I don't want to actually look at it. I just want it to go and do its things. I will run it in the Ubuntu images, and I am gonna give it a process bash, and I want to run the command line, and I'm gonna tell it to run less slash etc slash password so that I have terminal running. Looking at the password file, but I have got a typo right there. I typed lose the password file, so this is gonna work. It totally gonna crash. So later when I notice that it isn't running, I can go and look what went wrong with container logs. For example, lose command not found, and then I go fix it. Don't let the output of your Docker container gets really huge. This is one of those side effects of your convenience. It is very convenient being able to go back and look at it. And if you are writing tons and tons of data to the output of the process in your Docker container, you can really break down Docker to the point where your whole system becomes unresponsive. Stopping and removing container so you can kill or running container, and when you have killed it, it goes to the stop state, and when you are done with the container in the stop state, you remove it. So kill container dash name make it stop, and rm make it gone. So I am gonna run a container here. The same example we have seen several times. Okay, we got a container there. Over here I am gonna look at my running container. There I am running container. Now let's say I want this container gone. Docker kill container name. You can also kill it by ID if you want. Alright, look, I just got kicked out of there. Now if I run docker ps again and give it the name -i for the last container to exit, I can see there is my container. It exited 16 seconds ago. So let's go ahead and clean that up. When you are using container with a fixed name, if your letter wants to start the another container with the same name, you will very often get an error saying that container already exists. You can't use that name, and it's because you need to go through an RM to remove the old container. Stopped containers will exit until you explicitly remove them. One of the big features of the container is the ability to enforce limit on how many resources a container gonna use. You can limit it to a fixed amount of the memory. You can say docker run dash memory maximum dash allowed dash memory, and that prevents running container from clobbering the rest of the system. You can equally limit the CPU time. You can limit the relative. You can say give this container half of the total CPU time and the other one the other half, so that is one not busy. The other can use more CPU, but then it will enforce that they have the equal access. You can also give them a hard limit. You can say this container only gets to use 10% of the CPU total ever. Even if 90% of the CPU time is idle. Most of the orchestration systems that are covered in a later chapter generally require you to state the limits of the particular task or container. Now a few lessons from my bad experience and my good lesson 1. Don't let your container fetch their dependency when they start. If you are using things like Node.js and you have your node startup, and then when the container starts it fetch its dependency, then someday somebody gonna remove some library out from the node repos, and all of the sudden all your container just stop throughout your whole system. It's terrible. Fetch make your container include their dependency inside the container themselves saves a lot of pain. Also from the sort of different perspective, a little security hat here. Don't leave important things in unnamed stopped container. Don't do a week worth of work and just leave it sitting in a stopped container once your laptop, because you will inevitably come along and say my disk is full and I got a cleaning up sub stopped container, and then delete the seemingly unimportant container, and then your important stuff is gone. So be careful what you leave sitting around in your unnamed container. Docker is almost universally used to run network services such as web and database servers. To make this easier, Docker offers a wide range of networking options to connect containers together and to connect containers to the internet. For connecting them together, it offers private network where you can put each container on a network and they can talk to each other, but still be isolated from the rest of the container running on your computer. For getting idea into and out of the system as a whole, Docker offers the option of exposing a port or publishing a port. That makes that port accessible from outside the machine on which Docker is being hosted. Through the combination of these, you can wire up the network pretty much any way you want. To expose a specific port, use specifically the internal port that the program is listening on and what port it should be listening on the outside as well. If you would like what protocol to use, and there are as many more options, we are going to cover the fundamental here. Let's head on over to the terminal and you give this a try. Okay, over here in my terminal, let's set up the interesting but minimum example to show the flow between several containers. So over here on the left, we are going to start up a server. The server going to accept the data from one client and pass it to any other. Well and good, little more interesting than just one way, and then we are going to have the two clients on the right. So to start up the server here, we got this moderately long docker command. Let's break that down. We start off with a docker run and usual, then dash dash rm and ti for terminal interactive. As we are prone to do, here the interesting part, we are going to say dash p for publish, and we are going to publish port 45678 and connect it to port 45678. So here we just exposing the same port on the inside of the container as on the outside. It makes things easy to keep track of, but to make things a little more interesting, we are going to publish a second port 45679. And again, we will keep it the same on the outside and the inside. I am going to go ahead and use the dash dash name parameter here to give my Docker container an explicit name instead of just letting Docker choose an interesting but random one. I am calling it echo server. The echo is kind of line left there, and our usual example Ubuntu 14.04, and we will run a shell. Okay, note that I have got this container. Let's start up a bare minimum server. The netcat utility is great networking debugging program for just moving bits from one place to any other. It's super simple and good way to show off the networking without having to get concerned with anything else like starting a web server. So I am gonna to run nc for netcat-lp for listen on port 45678, but I want to take the output of that instead of just writing to the terminal here. Dash lp that other port we specified 45679, so that means that data will get passed into our system on one port and then spit out on any other port. Let's go ahead and connect some clients to that. Now over here on my desktop I have got netcat installed, but if you don't have netcat installed, don't worry. Docker can solve that too. We will just do get in a second. So I'm gonna to go netcat to the local host, to the place where Docker is exposing that port on port 45678 and connects to my other client. And see localhost port 45679 and let them send data. Alright, in this case the data went from this computer to a port export on this computer. Got passed into the container in one port, passed between two programs within that container, then passed back out to a port running on the host computer. Now I mentioned that if you don't have the netcat locally, then Docker can solve that problem. And that's a good example to illustrate one is the difference between using Docker directly on Linux Docker on Mac and Docker on Windows. So let's go over this little difference here just to illustrate that point. So I'm gonna go ahead and clear each of these terminals. Okay, so I have left the Docker server running here. We are not going to touch it. In fact, I'm just gonna to go up here and start listening again. Only listen once per connection. Okay, now over here, instead of running netcat locally just on the computer, I'm gonna to run docker run, and I'm gonna to choose an image that the netcat has the same ones we use for that server. I know it has dash dash rm dash ti ubuntu 4 dash. Okay, but who do we connect to? Localhost in this container refer to itself. We want to refer to the host computer. Now if you are running Docker desktop on the Mac, this is one of the cases where it's different. Containers are not allowed to directly address the container by IP address, at least not reliably. So they have added a specific host name for container to refer to the machine. This is the hosting them. The special name is the host.docker.internal, and then I can put nc host.docker.internal port 45678 and start that there. Now I am going to copy paste and change the port number to the second one 45679. Oops, I forgot to actually start the container. Docker run dash dash rn dash die ubuntu 14.07 dash. Okay, I'm gonna to paste it, change the port number. Here we go again. Alright, so that solves the problem of not having netcat. There's one more difference. If you are doing this on the window and don't have netcat locally, well, you can always install it. It is a very useful program, but Docker can solve that. So the difference is that if you are doing on this on window, you do exactly the same. Everything except instead of saying host.docker internal, just put the IP address of your window machine. Just put in the machine host, or if it has a DNS name, use that. You don't need to use the special name host.docker.internal on Docker desktop or Windows. No, explicitly setting the internal and external port number is very reliable. You always know where to find your service, but what if you want to run 12? Turn out Docker has that solved. You can leave off the host side of the port definition and Docker will fill in the form one of the available ports. This allows many containers running the same programs to share a same host. This is often used with some sort of the orchestration or discovery service like Kubernetes or something like that. Let's give it a try. Here I am back to my terminal and I am gonna to bring up the last command we used to run out echo server. But this time I am just gonna go ahead and remove one of the side. So here I am specifying only the port has seen from the inside of the container. I'm gonna to let the Docker choose the port on the outside. Okay, it's running nc-lp exactly the same command 45678 pipe lp 45679. But what port did it choose? Well, let's go to the Docker port echo server. That's why we gave it a name in that the last example so that we could look it up by name right there. Say port 45678 just happened to get assigned to the available port 32777 and 32776 for this any other one. So I will go ahead and say netcat localhost and I'm gonna to enter this dynamically generated external port 32777. Start up that side. Oh, I have a hit enter over here. There we go, 32777 and then NC. Localhost 32776 for 45679. Yep, that's right. 32776. Alright. Yes, it goes. Now, in addition to working with TCP as we did in our previous example, I just want to show briefly that Docker was just fine with UDP and other protocol as well. For publishing the port, you specify the internal port and the external port just like before. But if you put a protocol at end of UDP or TCP, then it will use those. So let's take a brief example at that. Okay, so here we are going to run slightly simpler version of this program just to make it quick. I will take out the second port and instead of specifying the internal and external, I am just going to put the internal port and UDP. So let's do the same thing but in less reliable network protocol. Okay, start it at running, but since it choose the port dynamically, I need to go and look up which port it choose. So let me do that again just like we did before. Docker port echo server and this time I see dynamically choose port 32771. So let me start something listening here and see dash u for UDP listen port 45678, hit enter and over here let's connect to that one and see that u for UDP localhost and again if you are using it on Windows and using a separate machine you would put your machine actual IP address there instead of localhost just as we did in the previous example and then I am gonna to put the dynamically assigned port of 32771. Hello world and over here we see that Docker works with both TCP and UDP. When we expose the container port in Docker, It creates a network path from essentially the outside of that machine down through the networking layer and into that container. That's very well. An other container can connect it to by doing out of the host, turning around and coming back it along that path. It's useful, but there are most efficient ways to go about it. Docker offers an extensive set of networking options for really controlling exactly how your container connects to each other and make sure that's secure just the way you want it. For that, let's explore Docker Virtual Network feature a bit and see what we can do it. Let's take a look at the existing network and see what's there by default. Docker network is so we can see three networks by default. Bridge is the network used by containers that don't specify a preferences to be put into any other network. Host is when you want a container not have any network isolation at all. This does have same security concern and none is for when a container should have no networking. Alright, let's make a new network just to play with. Docker network create, let's call it learning. Okay, now I have got a couple of terminal here. Let's put some machine on that network. Docker run the actual dash dash rn dash ti and know the interesting part dash dash net learning. Let's give it a name cat server dash name cat server. Names are very useful when using private network in Docker because different containers inside of the network can refer to each other by those names, so it makes it very easy for them to find each other. Now let's just finish that off with the usual bits. We are going to choose Ubuntu 1404 and run bash. Okay, we have the cat server running. Ping, I am gonna to clear that ping cat server. Alright, we can send traffic to ourselves. Is there anyone else here? Ping dog server, nope, no dogs here. Alright, over here, let's start up a dog server. Docker run dash dash rn dash ti and again dash dash net learning. I will put it on the same network so they can find each other and give it the name dog server and finish it off. Okay, now we can connect to that dog server from over here on the cat server on the left. Why? Yes. In fact, we can do it both ways. nc-lp. Oh, we can choose any port we want. We don't have to expose them in advance. I will choose 1, 2, 3, 4 over here on the dog side. Listen, and then over here I will do nc dog server port 1, 2, 3, 4. And let's say meow. And then on the other side let's say woof. So they can communicate in both directions, but that's just one network with two machines. Let's make things more interesting. I am gonna to start up a new terminal here. Let's make any other network. Docker network creates cats only. This is the network only for cats. Okay, now let's go ahead and put the cat machine onto the cat network. Docker network connect cats only and then cat server. Okay, now over here, let's make a thing a little more interesting. I will start up any other terminal, squeeze it down, rearrange things a bit, squish the dog server over to the side, put the cat server in the middle and over here on the left. I am gonna to start a new member of the network, docker run dash dash rn dash ti dash dash net, and this is where I am gonna to put on cats only dash dash name. Let's call it the Bobcat server. It's like the cat server only more ISO and run bash. Okay, so from here I can do ping cat server and get data. If I do ping dog server, traffic is not allowed. From the cat server in the middle, I can ping dog server, hit Ctrl C, yep, it work. And Bobcat server, no, over here on the dog server, we can still only make connection to the cat server. But we cannot connect to the Bobcat server because the dog server is not only the cat only network. There are many more options to this that give you a free grain control over here. We just show enough of the example to keep things interesting and to cover about 90% of the use case. The rest will left up to the experience. In addition to exposing ports and connecting containers together with virtual networks, Docker also have the legacy older way of linking containers together. It just use kind of like the private network scenario, but links are only one way, so you can connect from all the ports on one machine to all the ports together, but not in the other direction. It gives no information the other way. Also, secrets on the machine we link to, say environment variable with a database password, are visible to any machine that later come along and decide to link it to it. However, the result is not true. The server can't see environment variable on the machine that choose to link to it. Also, it may think depend on startup order, which machine is running in order for the other one to connect to it. It just makes orchestrating things a lot harder, and restarting container can be made or not to break things. If you are very careful, if you do it just right, it can be used correctly. I recommend sticking it the more modern option, so there are the cases where you really want the feature this offer. So let's give a quick tour. Alright, I am gonna to start up a server. It will be the variation on our cat server from previous example. We will have the docker run dash dash rm dash di the usual and give it a name cat server, and right in here let's give it a secret to keep. I'm gonna to give it the environment variable named secret. This doesn't turn the environment variable into some specific kind, it's just the environment variable named secrets to illustrate the point, and let's call it the interrupt love cats and then dash dash name cat server as we had before. Running bash and start it up. Okay, so the cat server is running. Now let's connect to it, and again with the variation on our previous example, we have our dog server here, docker run dash dash rm and ti dash dash name dog server. But we want this dog server to be able to connect to the cat server. So right in here I am going to add dash dash link cat server and then run it. Okay, so over here I will run a quick server and see dash lp port. Oh, how about 1234? Highly creative, and over here and see, and I'm gonna to connect to cat server on port 1234. Woof, and there it goes. They can reply meow. Let's try it to the other way. If I exit that clear board screen, over here on the dog server I am gonna to run nc-lp and port 4321. Over here nc dog server port 4321, and it just say whose dog server call links run only one way. Okay, now let's look at the secret experts over here on the cat server. If I run env, I see apart from bunch of terminal color setting that will be different for everybody at the top. Somewhere you will find the variable we set when we started it, secret equal the internet love cats. Okay, now if I run the same command over here env, I see that the environment variable has been copied onto the machine that linked to it. Under the name cat server, to tell which you container it copied from env, just say it was copied from the environment variable and the name of the environment variable on the other container, and then the secret content, but we did not see the environment variable from dog server on the cat server. Again, legacy things only operates in one direction. It is useful in some cases and you will encounter it in a great many existing products, and you can go ahead and use it there. There exists a very old form of linking that just set IP addresses in environment variable corresponding on the both side of the link. This one is basically totally unused and you should probably avoid in case where it is still turned up. We have used quite a few images thus far through this course. Now let's spend a little bit of time talking about how to manage and keep track of images we are working with. So you can list the images that you have already downloaded with the docker images command. It only lists the images you have already downloaded. It's not the tool for finding images to download. We will cover that later. So docker images, alright, I can see there are the several images on my machine. Now spend a little time, it is where it came from. The tag on it, this one has no name and no tag. The image I would mention before, I wanna mention this size here because these images share a great deal of their underlying data. You don't sum up these sizes here and get the total amount of space that Docker is using. In this case, all of these 122 megabyte images here are actually the same one 122 megabytes with different name on them. Docker is much more space efficient than it would like just from looking at this list, so don't get scared by that. So we have mentioned tagging the images on given name. I just wanted to mention that you don't have to manually tag images. When you do docker commit, it will tag the name images for you. So you can say docker commit my container id name. If I do docker ps-i to look at my most recently stored container, and let me put on my usual format argument here, I can say docker commit. I can use this id, cut, paste, and I would like to give it a name my image 14. Now when I run docker images again, I can see that it made a new image called my image 14 with a tag latest because I did not specify a tag. If I run that again and say my image 14 version 2.1, I have made any other image this my image 14 with a different tag. See, the version number came after a tag, and if you don't specify it, it just default to the latest. Alright, so the full structure of this name is the registry on the server that you get this image from, the port number on that server, your organization name, the image name, and then a version tag. You can leave out the part you don't need. Usually organization or the name is enough when you tagging your images unless you are using customer repo with the customer port or you have the version tag, so the images come from the docker pool, which is actually fun automatically for you to docker run. It available as a separate command if you need to do offline work or you wanna pull some images in advance. This doesn't come up that often. The opposite of the Docker pull is the Docker push, which we will cover soon. Now the images can build up very quickly. One time I cleared out all the old images on the server and freed up 500 GB. So if you are not careful, they can build up. The Docker RMA command for remove images take an image's name and tag and just move it from your system. In this just case, I'm gonna list my images and I have got a bunch of here. I don't need all of these. Docker RMA, let's start by removing this one. The completing unnamed unknown images that I'm never gonna use again. I don't even remember what is alright. No, I don't need this images. Copy Docker RMA, paste my images. No deleting all of these my images by hand. That's gonna get the little tedious. Let's talk about sharing data between container and between containers and host. Docker offers this feature called volumes. Volumes are sort of like shared folder. They are virtual disks that you can store data in and share them between the container and between the container and the host or both. So they have two main varieties of volume. They are virtual disks available within Docker. You have got persist one. You can put data there and it will available on the host, and when the container goes away, the data will still be there. And you have ephemeral volumes. They exist as long as container is using them. But when no container is using them, they evaporate. They will stick around as long as they are being used, but they are not permanent. They are not the part of images. No part of volume will be included when you download an image, and no part of volume is gonna be involved if you upload an image. They are for your local data and local to the source. So first, let's talk about sharing data between the host and the containers. These are the kind of link share folder you are used to when working with virtual machine systems, such as VirtualBox, and let's also talk about sharing a file into the container. It is very similar. I am gonna go ahead and make folder to share with my container. mkdir example, though I am in user author field, that's my home directory on this system. Of course, it will be different for yours. I am gonna go ahead and start a container to share that folder into the usual docker run -di, and here the new part -v, and then I'm gonna specify the entire path to my example folders /user/author role file /example. If you don't specify the entire path, this example will appear to work, but at the end of your data won't be there. Then after a colon, I am gonna specify the path within the container where the share folder can be found. After the volume specification, then I am gonna to put the image to start with, followed by the program to run bash. Now inside my container, I am gonna do ls/shared folder/ I see that there is nothing there. /shared folder/ my data. Now if I look at the shared folder, I see my data from within the container. Now when I exit the container, if I took at example, there I see my data. The data survived the expiration of the container that created it because it was shared with the host in a volume. By sharing a single file, it actually just the same. Just pass the path to the file instead of the path to the folder and it share a file. Just one little trick is make sure that the file exists before you start the container, or Docker will assume that it's going to be a folder or share it as a folder. Alright, now let's talk about the more interesting case of sharing data between the containers. This introduced the new argument to Docker run called the volume-from. There are shared disks that exist only as long as they are being used, and when they are shared between containers, they will be common for the container they are using them. So I am gonna run docker run -ti-v/shared data. So I am creating a volume for this container which is not shared with the host. To the docker run -ti-v/shared data, this creates a folder and I will run it on the Ubuntu. I will run bash. Alright, let's put some data in that shared folder. Typing on the keyboard echo hello output redirected to the /shared data/data file. Alright, we have some data there. So now I'm gonna to start up the any other Docker container. First let me look up the name of that container that I just started by running Docker. Okay, copy docker run --volume-from. This is the new part. I am gonna put --volume from and then paste in the name of the machine that has the volume I want to use. Ubuntu bash. Now if I go look into the -shared folder, ls shared data, I see that data file and I will add some more data. Echo more redirected to the shared data. Add more data. I will add some more data. Echo more redirected to the shared data and more data. Now if I exit the original container, my shared data is still there. If I start up the third container, do docker ps, find the name of that one. I see the name of it there, the adoring Lumiere. Typing on the keyboard docker run /volume-from the paste it. I looked up the name of the container on the left here. I have pasted right Ubuntu bash. I have pasted it to the right Ubuntu bash and into the folder of the shared data. I see the data here. This file, the data file originated in one container, was inherited by the second container and then inherited by the third container, even though the machine that created it is gone. Now when I exit both of these containers, this is the important part to understand right then. When I exit the last container using this volume, I went proof. Oh no, it's gone. That's what the volume are for. They are inferior. They can be passed from one container to the next, but they are not saved. They will actually go away. So we have been using a lot of Docker images without really talking about where they came from. Docker images are retrieved from registries and pushed through registries. Registries are piece of software and there are several options that you can choose if you want to run a registry. There is a piece of software that manages and distributes images. You upload images to them, you can download images from them, and they let you search to find the images as you want to use. Docker, the company, makes these freely available. You can also run your own as well. Many companies choose to run their own registry within their own company to ensure that their data stays safe and private. So let's talk about finding images to use. You can search straight from the command line with the docker search command. Docker search let's search for Ubuntu. You can see there is a lot of Ubuntu images, but one of them is significantly more popular than the other, and it's got the official flag, which means the Docker organization that runs this repo has verified that is actually from the Ubuntu organization. That sounds like the good place to start. Now, if you would like to take a web-based approach to the same thing, you can head over to the hub.docker.com. Give a search for Ubuntu here and see the same information, or perhaps we want to find a place to run Node from where the website here. If you click on it, you get a lot more information about how to use this container. They will list the available tag information about which one you should use. In general, when choosing an image, it's good to read through the readme.file and figure out how intended to be used. Once you have made an account, you can do the rest of the process from the command line. So the command is docker login, just that it will ask you for your username. I am their author on the Docker Hub and the password success. I now have an access token on this machine from my account on docker.io. Now let's push something. I'm just gonna grab and Debian images, give it a new name, docker tag the author, put your docker.io login name there, slash test images slash 14. Now I am called this version 99.9. Okay, docker push thereafter dash text images. Okay, pushing and push. Now I have published my docker images from all over the world to use. Couple of bits of device. One story I heard and fortunately haven't done myself. I do not push images containing your password to a Docker hub. If it there are several layers down, just not a good idea. Also, I learned to clean up the images regularly. One day I switched to a different computer and discovered that the container I was using to provide Java hasn't been available in the registry for months. It was really locally on my computer, and because I have not cleared my images, I had no idea what it is bending or something that wasn't still available. And there is a matter of trust, and there is a general concept when you are downloading the large blobs of things you did not build yourself. Be aware where you downloaded it from and you created it and how much you trust that person. Trust by occasionally verify. So far, we have made a couple of Docker images by hand and run things on them to make containers. Now let's explore building images with code. That's where Docker file comes in. Docker files are small programs designed to describe how to build a Docker image. You run these programs with the docker build command. So it's docker build and dash t stand for tag, and that just says when you finish building this thing. Tag it with this name so that it's easy to find afterwards. The dot at the end of the line is not punctuation. The specification the location where you can find the docker files. The dot says in the current directory, the place where you are running this command. If your docker file was somewhere else, you would replace that doc with the path to the actual docker file. When it finishes running your Docker files, the resulting images will be on your computer in the local Docker registry, ready to be run with the Docker run. So each step produces a new image. It's got a series of steps. Start with one image, make a container out of it, run something in it, makes a new image. The previous image is unchanged. It just says start from that, make a new one with some changes in it. The state is not carried forward from the line to line. If you start a program on the line, it's run only for duration of that line. So as a result, if part of your build process is download a larger file, do something with it and delete it. If you do that all in one line, then the resulting images will have only the result of that. If you download it on the line, it will get saved into an image. The next line will have that image saved there, and the space occupied by your big download file will be carried all the way through, and your Docker file can get pretty big. Be careful about having operation on larger files span line in Docker file. Let's take a look at what a Docker file looks like. Docker files generally look like this. They have lines. The lines have a command at the front and then some stuff after it. Run this, start from here, that kind of thing. And you can learn all about them at the official Docker file reference page on the Docker website. So each step of running a Docker file is cached. I mentioned that the later step don't modify the previous step. That means the next time you run your build, if nothing changes, it doesn't have to run that step. So Docker can skip lines that were not changed since the last time you build this Docker file. So if the first line in your Docker file is download this big file and save the latest copy, and then 20 minutes later you run that again, the file will have already been downloaded. So it won't run that line and it won't spend that time to go download that huge file again. This can save huge amount of time. You do have to be aware of it through, because if you wanted to re-download the latest version of that large file, you will have to explicitly make it do so. Just a little tip, put part of your code that you change the most at end of the Docker file. That's why the part before them don't need to be redone every time you change that part. One part I just can't emphasize too much is that Docker files are not shell scripts. They were designed with a syntax that looks like shell script because that helps them to familiar to the people and make it them a little easier to learn. But Docker files are not shell script. Process you start on the line will not be running on the next line. You run them, they run for the duration of that container. Then that container gets shut down, save into an image, and you have a fresh start on the next line. So you can't treat it like a shell script and say start a program on one line, then send a message for that program on the next line. The program won't be running. If you need to have one program, then any other program start, those two operations need to be on the same line so that they run in the same container. Environment variable do persist across line. If you use the env command to set them, just remember that each line in a Docker file is its own call to Docker run. Now let's build a Docker file. Let's start with the most basic Docker file that still are interesting. Make a file called Docker file with a capital D, and I'm gonna put this in it, and then I'm gonna build it and run it. Let's take a look. So first let me make a spot to put our example mkdir example. Alright, now let's go into that folder. Nothing there. I am gonna use a simple text editor, then no Docker file. Alright, the first line in a Docker file specify what image to start with. Where do we begin? That's from, and I am gonna start from an image called busybox. It is very small and it has nothing but a shell in it. Super tiny, and starting from the busybox I would like to run. So create a container, in that container run echo building simpler Docker image. Okay, after that run, it's gonna save it to an image. Then from that image it's going to set a cmd to run with its image is started. So when this image is started, I'm gonna have it run echo hello container. So now I am gonna exit, Control X. It asks me, do I wanna save? Yes, and I want to save it to the files Docker file. So I have made a Docker file. Now let's build it Docker build -t hello, just to give it to a name dot. Remember that dot? Very important. Alright, build pretty quickly. Let's go through what this did. It print out the step from busybox. It is created the image that we will be starting with 47 BBC. Don't have to remember these number. Step 2, it says starting from that image, creating a container, run this command. So it is said, okay, I am running in the container 55d7116 ... Alright, did that, and then running in that container. It's ran the line where I have echo building simple Docker image. There we see the echo ran and it wrote this to the screen while it was building. Okay, that container is done and it produced this image. Now it's saying that it's got an immediate container 55d71 which was created here to run our build step. It's saying nobody gonna use this. It is not referenced anywhere further down in the Docker file. So I am gonna go ahead and clean it up. See how this number matches that number. So it cleaned up the intermediate container and left this image. Now starting in that image, it's gonna to set the cmd to be run, and when this container starts, so it's updating the stage of the image. That resulting into the container called dd715 ... which then was committed to produce the image df9ec. And since no further step is going to use the container dd715, it said okay, I'm gonna go ahead and clean up that intermediate container, and the final result is the image df9ec3, which is the image from the last step. And then it went ahead and tagged it with the name hello. It doesn't print the tagging line right here. So now we have walked through the full build process from a very simple Docker file. Let's run it and see if it works. I'm gonna put the dash rm there so that it can clean up the container afterward. Hello container. No, let's make a slightly more interesting image which actually installs something in the image. For this one we are gonna start from the Debian instead of Visibus because we want to install things, and I'm gonna have a step that say update the latest available packages. Install nano, and we are gonna make an image that when you run it, it open up the little notes file for you to type some notes. Very simple, but it expresses all the important concept. So I'm back in my example directory. I'm gonna to edit my Docker file and change it to the more interesting. Instead of starting from the busy this time, I'm gonna start from the Debian version SID and the run step. Instead of just printing a little text to the screen or not actually doing anything, we are gonna add a run step that say dash y say don't ask me yes or no. Do I want to update? Just go ahead and say yes. Then once everything is updated, we are gonna go ahead and install the nano. Then we are gonna set the CMD to run when this container start. In this case, I am gonna use a different format for writing the CMD just so that we get a chance to demonstrate both format. This way of writing it is called the ESC form. Note that the comma there it's matter. This says when the container start, it will run the command /bin/nano with the argument /temp/notes to open it up in the editor. Let's save that. Just save it to a Docker file. Docker build -t example /nano. We started from the Debian version seed. Now it started a container called f24 ... and in that it's running apt-get update, doing a whole lot of work. Alright, down here it removed that container and it set the cmd or command to start with this image run /bin/nano/temp/nodes. Alright, and it produced an image we can use. Let's go ahead and run that docker run --rm so it clean up the afterward. And since I am running an interactive command inside the container, I want to run it in an interactive mode with the -ti example/nano. Note, I am not putting a command at the end like we have all in the previous example in this course because the command to run is backed into the image. Alright, I have some notes file. To make this more interesting, save alright and all done here. Now let's make an even more interesting Docker file. This one is gonna say start with a notes file with some content already in it. The important part about this one is that I am gonna to begin with Docker file by starting off where the previous example left. Instead of saying from Debian, I am gonna say from example/nano, which says start from the image I just produced in the last example and add more to it. This is kind of what makes Docker file cool. The way you can change them together to build on each other. I am back in my example directory. Let's make the Docker file more interesting. Instead of starting from the Debian SID, we are gonna start from where we left off. So now we are just gonna add a file called notes.txt to /notes.txt. Alright, so now let's change it so when this container start, we open our pre-created notes file. Okay, let's save that. Now nano-notes.txt, let's go ourselves started with a notes file. To do learn more about Docker file. Okay, let's build it and tag it example/notes. Alright, it started right from where it is left off. Added the file, set the command to run when the container start. Let's run it. I am gonna add the --remove here to clean it up, make it interactive and run example/notes. Alright, there are our first to do attempt to learn more about the Docker file. There are a great many more options available to Docker file than I covered in the previous example. So I would just like to briefly go through the rest of them here so that you will know about them when you need them. We saw the from statement which just said that what image do you start running from. This should always be the first expression in your Docker file. It's actually okay to put multiple of them in the Docker file. It means that Docker file produce more than one image, so they look like from Java version 8 build my image. The main trainer statement, this is a bit of documentation that defines who is responsible for creating this image and who should contact if it has bugs. It looks like main trainer first name last name. You can put middle name in there if you want and then an email address in the angle bracket. The run statement we encountered that says run a command through the shell. It also takes the command form which we will cover later. Run unzip the install.zip file into the directory or run hello docker. The add statement really quite a useful expression. We use it to add a local file, but it can do a whole lot more. It can do a whole lot more than just say add run.sh to the image at the location /run.sh. It can also add the content from the archive. So if you say add project.gz to /install, it doesn't copy the file .gs into the directory. It notices that it is compressed archive and it uncompresses all the file in that archive to that directory. So it automatically uncompresses .tar file for you. It also works with URL. You can add the thing that you download from the big URL to the project. That will call project.rpm to get download and put in the project/project.rpm. It is very versatile expression and well worth exploring. The environment statement sets variable both for the duration of the Docker file. So while your image is building and those environment variables still be set in the resulting image, you say env db-host db.production.example.com. A db port is 5432. The entry point and command statement that we use the command statement previously in the example. Entry point is much like the command, but it specifies the beginning of the expression to use when starting your container unless you take more on the end. So if your container has an entry point of ls, then anything you type when you use docker run my image's name would be treated as the argument to the ls command. Commands specify the whole command to run, and if the person when they are running the container types something after docker run image's name, that will be run instead of the command. Entry point gets added to when people add argument to your container and command get replaced when people add arguments to your container. You can actually use both of them together. If you have them both, they get strung together, one after the other. In general, if you are trying to make something that looks like a program and you want people to not care, it is running inside a Docker container. Entry point is for making your container look like normal program. Command is probably what you want to use almost all the time. Unless you are trying to do command and entry point and run can take a command to run into two different forms. The shell form looks like what you would normally type into a shell nano nodes.txt and it will be run in a shell. The escape form looks like the bnode/nano. Note the comma there, it is important node.txt and this causes nano to be run directly, not surrounded by a call to a shell such as bash. So it's slightly more efficient. In general, you can use whichever form looks better to you. The expose statement maps port into a container, expose 8080. We did this lot more in previous example where we said -p1234 colon 1234. Does the same thing. The volume statement defines shared volume or empirical volume depending on whether you have one or two argument. If you have two argument, it map a host path into the container path. If you have one, it creates volume that can be inherited by the later container. You should generally in Docker file avoid using the shared folder with the host because it means that this Docker file will only work on your computer and you will probably want to share it around someday or at least run it on the different computer. The work directory statement sets the directory both for the remainder of the Docker files and for the resulting container when you run it. It's like typing cd at the beginning of every run expression after that. So it is a useful expression to know about. You say work directory or /install, then all the rest of your run statement will happen in the install directory. The user statement say I would like the command run in this container to run as a user author, or maybe that user identify the number user 1000. This can be useful if you have shared network directory involved that is fixed username or a fixed user number. There are a great many more options. I have covered only a few of them that I want to be aware of right off the bat, but definitely head over to the official Docker reference page and look at the available command to the Docker file. They have spelled out here in the great deal more in detail and that I cover. When we build Docker files that go beyond the very simplest project, it often runs into the two competing desires. On the one hand, we want the Docker files to be totally complete, have everything required to build this project from scratch. So a year from now, we will be absolutely certain that we can rebuild it and then it will be have everything. And on the other hand, we want them to be super small, minimal and really quick to deploy. So people often do things like make two Docker files, one for their daily life and one for the production. These get out of the sync and stats ensures. So recently a new feature was added to Docker files called multi-stage builds. To explain how this works, let's start by making a small Docker files from Ubuntu 16.04 and run apt-get update to get the latest packages list. Then run apt-get-y for yes and install curl for downloading things during the installation process. Now we are going to run an example project that just call the URL https://google.com and pipe the output to the world count. It just counts the world -c to count the number of the character that we are going to save that into the build artifacts called the Google-size. So this just pre-calculate at the build time how big is the Google homepage in character And then when this project run, I want to display that information. So I'm gonna to add an entry point using the shell sentence echo Google is the big Google size. So when this run, it's just going to output its computer build project, which in this case is very tiny test file. Let's go ahead and run this and see if it is in action. I save head on over the same directory in my terminal. There I am. I see the Docker file, Docker build -t, and I will call this one too big. It's downloading Ubuntu, it's updating the packages, it's going to install curl. Still building? Okay, we have successfully built too big. The Docker image. The Docker run too big. Google is the big 220 character, but how big is that image? Docker images amongst my other images here. I see that too big is 171 megabytes, and all it's point out it's about dozen or so the character. Let's see if we can improve that. Back in my editor, I'm gonna to split this Docker file into the two parts. We're gonna to have the first part which will run largely unchained, and I'm just going to give it a name. So I'm gonna to say a builder. So from Ubuntu 16.04, using the name builder, do this step. Then down here, I'm just going to add the any other form that I'll find. I'm going to call copy dash add from equal builder, which is just the name I assigned above slash Google dash size, and I want to copy it through the same path in this new image Google size. Okay, save. Now let's run that again. I'm gonna to rebuild it. This time I will call it Google size. Okay, Docker run Google size. Google is the big 220 bytes, but how big are these images? Alright, we will see while too big cloud in at 171 megabytes Google size. The one we will just build clock in at 4.41 megabyte, drastically smaller for the same functionality, yet all of the ability to have the reproducible build is completely preserved. And now it is a story time. Long ago at a tech company right near you, I learned about Docker and created a Docker file for their new service. It ran fine in the production until one day the site was down. It was an emergency. My friend updated that image, saved it right over the old images, and everybody got on with their day. He was a hero. Nobody worried about how that image no longer matched the Docker file. And then my friend and me both moved on the new jobs and bigger and better places. And nobody was ever able to maintain that Docker file again. They just kept using exactly as it file like a golden image that nobody dares touch. It is a couple lessons I have learned from extracting golden images out of the enterprises. Step 1. Include the installer in your project. 5 years from now, the installer for version 0.18 of your project will not be still be available. Include it if you depend on the piece of software to build your image. Check it out your image gets good for that. Have a canonical building system that builds your images from scratch. That means starting from a base image with it has not been touched by anyone in your organization. Running a Docker file, build it up the thing that you can actually run in the production. Really avoid the temptation to log in one day, fix the configuration file, save the image over the same name, and get it back in the production. The first time you do that, you no longer have the canonical build, you have created a golden image. Docker make it is very easy to do that and very difficult to resist. Use small images. If you start with a very large operating system as a base for your system, that large operating system makes the larger maintenance, and you are gonna be shuffling around a lot of bits back and forth over the network that really are not being used. When you are building the image that you are gonna share publicly, say you ship your product as a Docker image, build it from the Docker file always. There is nothing like going back to an old version of the software that someone is complaining about the bug and having no idea how it was built and how it got that way. And just a little note, don't ever leave password hidden in the deep layer of your Docker file. It's trivial for someone to dig through and find them. And now let's introduce to talk about what the kernels do. Kernels are either part of the code or a respectable military rank or a Docker for every computer you interact with depending on your perspective. So kernel runs directly on a hardware. It has a bunch of jobs, most of which are pretty simple and very important. It receives messages from the hardware, new disk has been attached and network packet arrived. Everything that goes on electrically bubbles up the kernel and gets deal with it. It start and it schedule program. It says what's allowed to run, what, when, and it lets your computer do all the things you are asking it to do at the same time. It's control and it organizes the strong devices on the computer. When you say write to this file, the kernel says, when he said write to the file, he actually means this latest part on the disk. And it goes there and writes the data. Someone has to make their decision, and that's the role of the file system inside the kernel. It passes the messages between the program. When two programs in the computer want to communicate or two programs on a different computer want to communicate over a network, they ask the kernel to pass the message. The kernel passes a message, get it ready, send it over the kernel on the computer, which receives the message, get it ready for the program and send it to the program over there. It allocates resources, memory, time to actually do work on a CPU, how much network bandwidth to give to who, all of that stuff is managed by the kernel. And Docker is a program which manages the kernel. So Docker is well three things. It's a program written in Go. Go is a nice upcoming system language and its job is to manage several features of the kernel and use these features to build the concept of container and images. So Docker primarily uses C groups of control groups to group processes together and give them the idea of being contained within their own little world. That's what keeps one container from interfering with any other. It's using namespaces, which is a feature of the Linux kernel, which allow to split into the network stack. So you have one set of address for one container, any other set of address for any other container, and other addresses for things that are not in container at all. It uses copying on write file system and various other approaches to build the idea of an image to say you have this image. It doesn't change, but you can run stuff on top of it, and people have been doing this for years. Honestly, almost none of what Docker does is truly new. They took things that people were working very hard to do and they made it very easy, approachable, and they created a language around it for people to talk about it. And they made these things popular. So what Docker really does is make script distributed system easy, and that's why it is offering weight of it is. These things that used to be the realm of very large enterprises with enormous budget are now easily done on any one computer. Of course, you have to have a fairly peculiar definition of the word easy. So Docker is dividing into two programs. It's the client and the server. These two programs communicate over the socket. That can be network socket where the client is running on one computer and server is running on a computer somewhere on the cloud provider across the world. Or they can be running directly on the same hardware, or they can be running on the same hardware with a server in a virtual machine, which is a common case for people doing this course. In that case, the client communicate over the network and send message to the Docker server to say make a container, start a container, stop a container, that kind of stuff. When a client and a server are running on the same computer, they connect through the special file which is called socket. And since they can communicate through a file and Docker can efficiently share a file between host and container, it means you can run the client inside Docker itself. So the traditional Docker scenario with a single host, you have Docker the program connect to the socket, send command to the Docker the program, which is the server side, and that's create the container or delete the container, all the rest. But it is pretty easy to run the client inside of the container and share the socket into the container, which allow the same messages to go through the same socket, get to the server running on the host and do everything that it will do normally. So let's take a little look at what it looks like in practice. The idea is to get feel free to what it means to control a Docker through its socket. Now let's take a look at the Docker control socket. And as we can see, it's just a file. If you write the proper data into the file in the right format, then it will cause the Docker server to do things. If you follow along with this code from the Windows machine, this file won't be directly accessible through it is still available from other Docker container. Next, I am gonna run the container client inside the container and give it to access to the Docker control socket on my computer. Docker run -ti -ram so it clean up after itself. Then the volume mount where I mount /var/run/docker dot socket into the container under exactly the same path. So we have given the Docker container as a hook for its client to control its own server. Then I am gonna use the image name Docker provided by Docker, the same company. We will just run a shell. Now that it's downloaded the image, let me clear the screen and let's look at the Docker info. Yeah, we are running the Docker run -ti rm ubuntu bash. So now I am starting any other container from a client within a container. And here I have it. Though this is not a Docker in the Docker, this is a client within a Docker container controlling a server that's outside that container. This flexibility is where you control Docker from is the one of the key idea behind the Docker and has been major contributor to its success and popularity. One of the main things Docker does is manage your networking for you to create container. Let's take a little brief look at the some of the things Docker does for you. First of all, networking is divided into many layers. The bottom layer is how machines that are near each other or containers that are near each other actually talk directly to each other. We call this is the Ethernet layer. It moves little frame of data into the local area. Above that you have the Internet Protocol layer or IP, and that's how data moves between network and between systems in different parts of the world. Routing is how packets get into and out of the network. Docker take care of the setting up that for you. And ports, when we talk about the ports throughout this course, we are talking about specific program running on a specific computer, actually listening to traffic. So Docker uses bridges to create the virtual network inside your computer. When you create private network in Docker, it creates a bridge. This function like software switches, it's equivalent to have a little blue box on your desk and plugging a bunch of different wires into it. Except it's all within your computer and you are plugging container into with the virtual network wires. So these are the used to control the Ethernet layer container that actually talk directly to each other. Let's take a look at these bridges inside the running Docker system. So in order to actually look at this, I am gonna need a system with the BRCTL or the bridge control program installed and access to my Docker host networking. Because we have Docker, I don't need to worry about this. I can do Docker run dash and h and the usual TI. I gonna put a dash dash rm in there so I don't have to clean up afterward. And this bit here where I say net equal host, give it to the full access to the host networking stack, turn off all the protection. And I will start with the Ubuntu 16.04. Okay, I am gonna start that up, apt-get update, and once that finishes, apt-get install b-r-i bridge utils, and we wait it a little while that run and know that's has been done. I'm gonna run brtci show and we can see this system has a couple of bridges on it. One called Docker 0, which is the virtual network used by all machines in Docker that don't have their own network. If I go over to this other terminal and create a network, Docker network creates my new network. So Docker created a network there, and if I look at the bridges on here, I can see that a new network just showed up. In fact, looking at the beginning of the network ID, that is the 18D34CBA, that matches bridge 18D34CBA, that's the bridge that corresponds to my new network. So Docker is not magically moving packets between the container. It's creating the bridges by running command to configure your system. And I turned off the isolation that prevents container from messing with the hours network by passing the that just net is equal to host option. It is very useful for learning and debugging, and probably not a good idea to have it turned on for the production. So our next layer up is how Docker moves packets between network and between containers and the internet. It uses the built-in firewall feature of the Linux kernel, namely the iptables command, to create a firewall rule that controls when packets get sent between the bridges and thus become available to the container that are attached to those bridges. The whole system is commonly referred to as NAT or network address translation. That means when a packet is on its way out toward the internet, you change the source address so it is back to you. And then when it's on the way back in, you change the destination address so it's look like it came directly from the machine you are connected to. You can look at these for your container with the command sudo iptable -nl and t for table. Let's take a look at how Docker accomplishment port forwarding under the hood. Now let's take a first-hand look at how Docker actually gets the packet into and out of the container. For this, I am going to need a couple of programs, namely the iptable utility, to be the available, and that's what Docker is so far. I am going to run a Docker container that will provide me these tools, Docker run -ti as usual, -rm, so I don't have to clean up after it, and this is one here, -net equal host. It gives this container direct access to the networking. Then I am gonna need to further turn off these safeties by running that privilege equal true, which lets this container have the full control over the system that the hosting. Then I am gonna choose the Ubuntu images because it can easily install the tool I need. So we'll start in a bash shell apt-get update. Now I am gonna to install iptable apt-get install update. Yes, okay, now let's take a look at the networking on our host iptable -n-shell for list -t-net to show the network address translation table. You will see here we just have the default entries. Now to make things interesting, let's start up the container with some ports to forward the Docker run -ti -rm. Now we are gonna add a -p to map port 8080 on the host onto a port 8080 in the container. And again Ubuntu and bash after starting up the container. If I go back into my privileged container and I run the iptable command again, now we see that we have a port forward rule that say forwarding anything with destination port 8080 to the Docker container IP address on the port 8080. So as we can see, exploring port in the Docker is really just port forwarding as a networking layer. So exposing a port is really port forwarding. Namespace are the feature in the Linux kernel that allow you to provide complete network isolation to the different processes in the system. So it enforces the rule that you are not allowed to mess with the networking of the other process. Processes running in the container are attached to the virtual network devices, and those virtual network devices are attached to the bridges. Will let them talk to any other container attached to the same bridges. This is how it creates the virtual networking, but each container had its own copy of all the Linux networking stack. All of the different pieces that make up the networking are the isolated to each container, that they can do things like reach in and the reconfigured other container. Namespace enforce the rule of container and keep containers safe from each other. One of the Docker jobs is to manage the process in the container. Keep them isolated and keep them talking to each other where appropriate. First, a little primer on process in Linux. Processes come from the other process. It is a parent-child relationship. Just one parent through. When a process exists, it returns that packet to the process that started it. And there is a special process, process 0 called init, that the process that started it all, and every other process in the Linux system comes from dividing the process into the other process. So in the Docker, you container start with one process, the init process. That process can divide into the process and do any number of things. Often it starts with a shell, and that shell split off and run command and run other processes. And when that init process exits, your container just vanishes and other processes that were in at that time, the init process exits gets shut down. A container is done. Over here I am just gonna start up the example container. Docker run dash di dash cleanup after yourself. Now I am gonna give it a name. That dash name is hello, and then I will run ubuntu and run bash within that. Okay, now that it's running, I want to find out what is the name of the root process inside this container, and it is a convenient way to do that. It is doing with the docker inspect command. Docker inspect is an incredibly powerful way to find out any piece of information about a program programmatically. It provides this jQuery like syntax that you can use to drill down through the data structure of that container and extract any information you need. It is very useful when secreting. So when I'm gonna run docker inspect that just format and say I only want to find out the process ID, PID of the main process is the container. So I am gonna get state PID, and then I would like to apply to the container with the name hello. And I get out of the process identification number. Let me just copy that to the clipboard here. Now I am gonna start up a super privileged container with the most of the safety turned off so that I can use it to kill the process in the underlying host without being stopped by Docker. I am gonna run docker dash run with the usual TI and clean up after yourself. Now I am gonna pass privilege equal to turn off most of the safeties and PID host. To turn off the even more of the safety, then I will start with Ubuntu image and I run it in interactive bash. Okay, now that is running. Let's kill that process and watch what happened to the container over here. Bang! That container is done, and very important job of Docker is to control the access to the limited resources of the machine. That's the amount of time the CPU can spend doing things and amount of memory that can be allocated between the container. These limitations are inherited, and this is very important of the container is given a certain amount of memory and CPU time. No matter how many processes start, the sum total of these processes can't exceed the quota that was given to the initial process. They can split up differently amongst themselves however they would like, but you can't save your limit from starting more process in order to consume more limits. Now let's talk briefly about how Docker accomplished the idea of images and containers. How does it do the storage behind them, keeping them isolated, letting them be stacked on the top of each other. All of that step requires a little bit of an introduction to the layers of Unix file system method. So at a very lowest level, you will have actually things of that store bits, hard drives, thumb drives, network storage devices, thing where you can set a value to 1 or 0 and it will remember it and you can come back later and get it. The kernel manages these. On top of those, it forms them into the logical group. So you could say these four groups from array to array, or these two drives should be treated as one drive, or this one drive should be treated as 432 drives. So it has a layer that lets it sort of partition of drives arbitrarily into groups and then partition those groups up. Docker makes extensive use of this capacity. On top of that, we have the file system that determines which bits on the drive are part of which bit of file. So the fourth byte in the file for 2.txt will be the particular spot on the particular drive, and it's up to the kernel with the file system to keep track of where that spot actually know. On the top of that, you can take program and programs can pretend to be a file system. We call this fuse file system. So with that in mind, the secret to the Docker and all of its images is code. All about code. Code is an acronym. It is case for copy on write. So we start with our base image. This is a code. He has no spot. No, I want to write some spot for this code. Let's give him some dark spot. You know, good traditional code spot. Instead of writing directly onto the code cause someone else might be working with this code, there might any other container running off this image right now. I don't wanna just reach in and write some spot on the image because someone else is probably using it. So I write my spot on a separate layer right next to it, and then when I start my container layer the spot over the code and give that to the container. So the container sees the image of a code with spot even though the code image still exists without this spot, and the other that are still using the spotless core images can continue to do so, but I want these dark spots. No, somebody else really has the more artistic perspective. They would like a core with little spot, so they are gonna start with the same image. literally the same image, not a copy of image, but with the same one. And they are gonna make their own layer, but their own interpretation of what course part should look like. So they will make their own file system layer and layer it over that image. And here we have a code with different color spot, so it is called copy on write. When I would write to this code, instead of writing directly to the code, I write to my own layer which gets layer on the top of the code. When I wanna look at the code, I just look at the whole thing. I only copy the piece what I write. I did from the original file and copy when you write. So get a little bigger perspective, we have the original image of the code and change just one of them. I am gonna draw him down here. We have the two resulting images of that code, each one has a different set of spots layer on the top of it. So we have a total of 1, 2 or 3 images here and two combination of the way they are layered. Docker has many different actually in kernel mechanism and it using for managing the code layer, the copy or write file system layer, and these depend on lot what's available on the system it's running on. Sometimes it's using BTRFS, sometimes it's using LVM, the logical volume manager, sometimes it's using the overlay file system. There are many ways. It doesn't really matter as long as if it can accomplish layering on this own sort. You don't have to worry about the format of code on one machine, a copy on write file system if you wanna import that image to any other one, because it take the each layer, split out the layer and make them into a normal GZIP file and ship them over the network to use separately, and receive end of that network connection, the place where you are actually running of the Docker server, receive all of those layers separately and then put them together using the file system that are available on the computer. So this how code can move easily between computer. So the container are independent of the storage engine. I can send images between the machine pretty much freely. There is one little bit depending on the storage layer that is used on a particular machine. It is possible in some cases to run out of layer. Some of the storage engine have a limited number of layers and others don't. If you make a very little deeply nested images on a machine that allow a great number of layers and then you package it up and try to download it on the image that is using a storage engine with less layer, you can run out layer. This is worth being vague aware of. It doesn't come up very often and it's good to be able to recognize it when it does. Any other part of images and a storage in Docker is how we do volume and share folder with the host. They are not actually magic, they are built right into the Linux file system. So the Linux file system starts with the assumed root directory called slash. Everything is slash something slash home slash author slash etc slash configuration file. They will start with slash. Slash is the root of the trees where it all starts. You attach devices to the various point along the tree. You can also take a directory from everywhere in the file system tree and just attach it somewhere else right on the top of what's there. Let's take a look at that. To watch bind mounting in action, I need convenient Linux system to show it. Well, that's what Docker for. So I am gonna to go ahead and spin up the Docker container to work in because I want to manipulate the file system. I'm going to need to exceed the default permission for a Docker container. So I'm gonna have to pass the dash dash privilege equal to my container so that I get a container that I can do this example in. And as usual, I'm gonna pass dash dash di and rm and let's run in ubuntu and bash. Okay, here I am in my container. Let's make a directly mkdir example. Okay, cd example. No, let's we are in our example directory. It's brand new, nothing here. Mkdir work. This will be my pretend working directly. Cd work. I'm gonna do some work. Work involve making files. So I'm gonna make some file a b c d e f. Looking at them, there they are no. I'm gonna head back to those base directory. Now back in the base directory, I'm gonna do some other work. Mkdir other work. Okay, cd other work, and I'm gonna create other A or other B, other C or other D. Looking at them, there they are. Now I am gonna go back to the example directory. Here I am in example directory and if show all the file that we have work and other work with A, B, C, D, E, F in the work and A other, B other and C other, D in the other work. Alright, very straightforward here. Now what I am gonna do is I am gonna run mount on to manipulate the file system. Dash O bind to say attach one directory on the top of the any other. Then other work on the top of the network. Now if I do ls dash capital R to show all the file, I see that other work contain other A, B, C, D, E and work now has been content of the other work layered on the top of it. Other A and other B, other C and other D. Again, it did not copy these, it just took the directory that contained them and attached it to the file system right on the top of the work directory. It also did not delete them. They are still there, they are just previously covered up. We can uncover them by running the umount command and unmounting work. Okay, now if I do ls dash capital R again, we see everything is back by way it was. They were just temporarily covered by any other directory. So there is an important side effect of this which you have got mount order correct. If you mount a folder and then a particular file within that folder, you have to do in that order. If you mount the file, so it bound mount that file right onto that position, and then you mount the folder on the top of it, the file will be underneath the folder and will be hidden. So it is important to get the order of the dash v for the volume argument to the Docker correct. Any other bits is the mounting volume. Always mount the host file system over the guest. Docker does not give you the way saying mount this guest file system into the host preserving what was on the guest. It always chooses to mount the host file system over the guest file system. As we start exploring building larger system with a Docker, one of the first questions that often come up with where is my data? Is it safe? Many companies choose to run their own Docker registry so they can know their data is safe and somewhere they can protect it. So it's just a program. You can run it anywhere your program to run using existing infrastructure. It stores layers, images, keep track of them, storage the tags, generally the metadata around the images. Along with the images and just the service that listen on the port 5000 for instruction like push this image and pull that image, load this image from a disk, a search for image containing these keywords. It also keep track of who allowed to log in provided that you have configured that. There are a couple of popular choices. There are official Docker registry produced by Docker. The company and the most popular having caching repo. Next is also happen to provide in the newest version a Docker repo built in, so there is a good chance you already have a Docker registry running in your organization and nobody using it. Now since the registry is just a program designed to provide a network service, why not go ahead and run it in Docker? So Docker make installing the network service is pretty easy, that's what it's for. And the registry is a network service, so let's just run in Docker. All we have to do is a docker run dash d for detach, which we have seen. I want to export port 5000 in the registry to port 5000 on my local machine. This is new argument dash restart always say if this container die, just restart it immediately. We give it a name registry so I can keep track of it and the image to use it called registry. Version 2 is a current, okay, no it is running. No, just to show what this does, let's push something to it. So the first thing I'm gonna to do is add a tag to my image to associate with the local registry that I have just started. So I'm gonna to run docker tag. I am gonna to take my Ubuntu 14.04 image that happen to have locally. You can choose any image you like and I'm gonna to tag with it first. The name of the server running the registry, which in this case is localhost, and I'm running it to port 5000 slash a name for organization or namespace. I choose my company and the image name is my Ubuntu version 99. Now I'm gonna to go ahead and push it to my registry. Now I have a copy of my Ubuntu image saved locally. So regardless of what happened to the official version, I will always have a copy of this one. Having saved things locally has really saved me a couple of times. When images I expanded on the disappear from the main repo, one thing to know, you must set up the authentication and security on this registry before you expose it to any network, especially the internet. To do that, head over to the official Docker registry documentation page, giving the introductory material later once over, and then head over to the deployment instruction for detail on setting up the authentication and choosing where your registry is going to permanently store its data. There are several options for preserving your images. One of them just stored it on the same machine that's running on the registry. You have that machine backed up, good solid backup regime, they work fine. One of great option include a Docker trusted registry made by people who make Docker, or if you are on the Amazon ecosystem, the Elastic Container Registry integrates nicely with the rest of the AWS services. And the Google provide a Google Cloud Container Registry which tightly integrates with the rest of the Google ecosystem. And on the Microsoft side of the thing, there is the Azure Registry Container, which is an excellent option for the service that need to integrate with other things using Microsoft Azure. Another important option is saving or loading your images locally without using a registry at all. Docker offers a pair of commands, Docker save and Docker load, to do the obvious thing. So let's look at the images I have here. Now I am going to save my most important images into the archive so that I will have them available. Docker save -o for output. Then the file name, I am naming the file my images.tar.gz, and I am gonna put the images debian colon seed busyboss and ubuntu 14.04 in there. Debian seed busyboss, and since I did not specify a tag, it will use the latest and ubuntu 14.04. Saving your images locally is a great way to make them available when you are traveling. Making backup and a good way to ship images to the customer, and never underestimate the bandwidth of 747 full of Docker images on the backup tabs. So now to show that actually worked, let's go ahead and delete my local copy of those images. We see that they are gone. Now I'm gonna to say docker load -i for input, my images.gz, Docker images, and we can see they are back. The Docker save and load command are also very important for following you to move images between storage type on the same server. If you switch back and storage engine in Docker, you have to save the images out, the load them back in after switching, and it is also really a good way to get your images to the other people literally by mailing them. Now let's briefly touch on how large systems are being built using Docker today. So just to start with, one container is about useful as one hand clapping. It's cool, it's philosophically neat, maybe you can get something out of it, but most people want more. There are many options out there for orchestrating large system of Docker container. We are just gonna touch on a few and give you a place to start. Orchestration system start your container, keep them running and restart them if they fail. They also allow the container to find each other. If a container gets restarted, all the machine that were connected to the need to be able to find its replacement. So service discovery is a big part of any Docker orchestration system and making sure that the container are running in a place where the resource exit them to actually do their job. If the storage they need available at that location is there enough RAM, is there enough CPU, is that the image being taken offline for maintenance, does this container need to be moved somewhere else? So the easiest to get started with is the simplest is the Docker Compose. For single machine coordination, there is a de facto standard. In fact, you already have it in your computer. It's designed for testing, development, tagging, generally working on the project that have more than one container, but not for serving them in a large scale system and not for things that scale dynamically. What is that is bring up all your container and volume etc. with one command. You just run Docker Compose up and install all your containers. Now for larger system, there are many choices. I'm gonna touch on a couple of them here and talk about the compare them. Kubernetes bring a couple of ideas that are fairly common to all of the orchestration system but expressed differentially everywhere. It has container which run program. There are container in way that we actually think of them. Pods are group of containers that are intended to be run together always on the same system. So pods give you approximately as much as Docker Compose but is dynamically distributed. Kubernetes find a place to run it and it provides orchestration and services discovery and all the other stuff around these pods. Kubernetes had the idea of service which make pod discoverable by other, accessible to other. If a connection to a pod at a part of service get restarted somewhere, that service will redirect the traffic to a new instance. Kubernetes have an amazing powerful system of label for describing every aspect of our system. So you can say my service need to connect for the instant version 5.2 running on this hardware and I need an existing that is the same data center that is the other service. It is very extensive. The Kubernetes command made scripting large operation in Kubernetes if not easy possible to that extent that other system don't. It gives you a sort of one command interface to do almost everything with Kubernetes and it provides a very flexible system of overlaying network to allow your container to find each other. Regardless of how things moves around throughout your infrastructure, Kubernetes run equally well on your hardware or on your cloud provider or even across both of these. Its overlay networking system is quite well suited to a wide variety of deployment scenarios and it has a service discovery built in. To get started, head on our kubernetes.io, head over to the documentation page and click to get started. And the other great option is the Amazon EC2 Container Service or ECS. This service uses the analogous vocabulary but with a slight different twist to each part. Task definition provides all the information required to start a container and set of containers that are designed to run together. It's somewhat analogous to a pod a little bit in a Kubernetes. It's all the information required for services it will run together on the same machine. It doesn't actually run anything creating a task definition, just define a task that will run. When a task definition is actually run, it's called a task and that's the bunch of containers that are running right now, shared together on a single host. Services that take tasks, expose them onto the net as a whole, and ensure that they stay up all the time. So you will create a service, have the 14 copies of particular task, and it will ensure that many copies is running all the time, even it has to be split across several hosts. ECS has a bunch of advantages too. It ties onto the existing Amazon infrastructure very well. So Amazon Load Balancer ties into ECS service to make your traffic available to the internet using the existing system. You create your own instance in the AWS. You have lot of control over that, and once you get in the instance running, you run an agent on them and call them to join the cluster. This is kinda cool because you take the Docker control circuit pass into the agent and then you run in a Docker and that allows the agent to control the host that is running on. Kind of the niche system that making running EC2 cluster very convenient from an operational perspective. ECS provide a set of Docker repos built in, so you don't have to run your own repos. ECS has built them in and they are made readily available. And they made available to the machine on ECS. It's perfectly easy to run your own repository along with ECS. You don't have to use the built-in ones if you have already on your own. Container and tasks can be part of cloud formation stack, which made deployment along with the resources in AWS very easy. So if you have the container that need to access into queues, they need access to ECS2 volume, you can deploy all of this in one go and have it cleaned up together when the services end. To get started with ECS, head over to the Amazon ECS product page and click on getting started. Other popular option including AWS from the Amazon, which is more automated version of AWS ECS, Docker Swarm from the people who make Docker, Google offers Kubernetes engine and Microsoft offers Azure Kubernetes services for orchestrating your container. Note that we have looked at Docker orchestration from a theoretical perspective. Let's just have a brief tour of using one of these systems. Here I am Amazon Web Services console in the ECS service where I have already configured a cluster. I would like to show you what it looks like to use an existing cluster to deploy something with Kubernetes. So here in the console I see I have a cluster, but I don't see anything else. With Kubernetes you do essentially all of your interaction with it through the command line. So here I am in command line. I'm gonna run kubectl get services and I see that my cluster is not running anything. It's running only its own management service. Now let's go ahead and deploy something to give you an idea of what it look like. Over here on getting started page for ECS, I have already gone through the step of getting up the cluster and going the authentication to work between my computer and this cluster. And down here at the bottom we have launching an application. Let's go straight to the fun part. Everything in Kubernetes have that application controller and the service. The application controller job is to make sure that this service is up when it need to be. So we are essentially going to create a bunch of services. First we will create the application controller for each, then we will create the actual service. So I am gonna start by copying this command here, which is going to call kubernetes apply and then a path to the controller definition. And we see it created the Redis master controller. And now I am gonna create a Redis service kubernetes apply and then again we just pass a path to the configuration file. In this case the configuration file is on the web, but it could just and easily to be setting up on the computer. Okay, we have created one of the service, creating the next application controller and next one. This project has a few services that all work together to provide a sample guestbook application, the classic Kubernetes example, and then I am gonna to repeat the process a couple more times with the rest of the service in this application. And now let's see if it is work. I'm gonna ask Kubernetes what services are running. And there we go. No, because my screen is narrow, it's cutting off the full DNS name of my service there. So I'm gonna run it again with the wide option so I can get the whole thing. Okay, let me just open up a new tab here, paste in the DNS name that was created for my service and add the port number 3000. And this may take a minute to operate because the DNS name may still be propagating across the internet. You might get a DNS not resolved for the first time or first few minutes. So then it's actually pick up the right after that, and there we have it, our guest book service is running. Let me sign in. No, I have got the running, tried it out. I am just gonna go back to the command line and I am gonna delete it so that it don't run up too much of Amazon bill. So again I use the kubernetes command to delete all the things I just created. I am gonna delete the Redis master, Redis slave, the overall guest book app, and then I am gonna delete its backing data store, the Redis master and the Redis slave and the service for the guest book itself. Clean it all up and now I can see my cluster is back to running nothing. To get a little more variety in Docker deployment, let's go deploy a basic web application using Google's hosted Kubernetes option. I'm gonna start here at Google Kubernetes Engine Quick Start Guide. Quickly move through here. I'm gonna head over, create a new project. Let's call it Learning. Select, click on Learning or right click on Kubernetes Engine. Once this is ready, you might get a question about enabling Kubernetes Engine. Click enable if it show you that if you have already used Kubernetes engine then it doesn't display it. One other tip while we are waiting here, if you are logged into a multiple Google accounts, it can be very confusing when you switch between the project tab. Which one connected to which account and following link can something jumps account. I am gonna go ahead and click on the activate Google Cloud Shell. That just provide a very convenient virtual pre-configured environment for using Kubernetes. Pre-configured, no, back to the quick start guide. I need to go gcloud config set project to the project ID which is printed right above it. Conveniently, alright, set zone, and I am going to choose the example zone of US West 1A. Now I am gonna use the Google Cloud Console to create the Kubernetes cluster create. Control Alt clear the screen in the setting as well. Cloud create cluster, I will call it learning. Okay, and creating the cluster does take a few minutes. Okay, now that my cluster up, let's use it. I'm gonna configure the login credential in my cloud shell. Here we use the cluster gcloud container cluster get conditional learning. Okay, now that I have created a service, let's expose it into the internet. Initially services when they are created within the Kubernetes network. Then if you want to attach a pipe to them from the internet, you create a load balancer that will direct traffic into it and out of the service. You could do that with the kubectl expose. In this case, run kubectl expose deployment hello server, the name of the server I just created. I would like to use a load balancer to direct traffic to port 80 on the web port 8080 within the service. Now let's take a look and see if it is ready. Tech get services hello server. Ah, there we see it up. It is ready and it has external IP address of this one right here. Alright, let's open a new tab, set in see if it works. Tada! There is a lot more to Google Kubernetes Engine. This has been the sample to help guide you choices as you choose where to go next in the learning Docker. So one more thing before we go, let's just clean that up so that I don't get billed too much for it. Control all to clear. So delete it the hello service and I can shut down the cluster that I use to run it. Yes, I'm sure I right now that's all clean up. Thank you for watching this video with me and I hope you had as much fun watching it as making it. The next step is set a personal goal. Get one service that you work with anywhere to run in Docker. Then go learn about making Docker files. It is a great place to expand your knowledge of what's including in this course. After that, see you if you can run a production service on your laptop and then maybe go tell your co-worker about it. A fun project is to make a personal software development image that has all the stuff you need to do your job so you can download it from any server you happen to be working with. Have all your stuff right there. Thanks for watching this video.